Hi, this is Dr. S.P. Harsa, Associate Professor in Mechanical and Industrial Department, IIT Roorkee. I am mainly teaching the design related courses like solid mechanics, like machine design, and for the higher studies, I am mainly teaching the dynamics of mechanical systems, mechanical vibrations, and like the other courses like synthesis of mechanism and all. This course, which is developed under the National Programs on Technology Enhanced Learning (NPTEL), mainly dealing with the vibrations and the control strategies. We know that mechanical vibration is one of the key issues, because whenever we are running any machine, or even when we are traveling to a train or any vehicle, or even when we are dealing with the human body, we know that the dynamic phenomena is always being there. And when we are trying to analyze these dynamic phenomena, we know that until unless if we are not able to analyze the physics involved in those kind of excitations, means the vibration related issues, then we cannot analyze seriously what kind of like the signal generations are there, or what kind of like the these responses are there. So in this course mainly we are going to deal with the vibration related problems, that you see what are the basic causes of the vibrations in any of the machine. And then you see if we know that the vibrations are there, even if it is a new machine or the robust design is there, then how do we control? So what are the parameters which we can control, like which are executing the vibrations in the machine, and what are the the limitation of those things through which you see here. Say you see here, we know that when we are traveling through a machine, traveling through a train or a bus or even in the aeroplane, we know that there are certain excitations which are always creating some kind of the discomfort to human being. What are those like the excitations? Why these excitations are coming? Even when we are traveling through a local train, or when we are traveling into, say, in Indian conditions, we have like the Rajdhani, the vibration levels are different. So why this is so? What exactly the design features that you see the vibrations are being damped out, or even you see they are controlling? So this course mainly divided into 4 main categories. One, we need to understand basic principles involved in the vibrations, means the physical significance of those parameters through which the excitations are coming. Second, you see here what are the control strategies. There are 2 main methods broadly classified. One is the passive controls, in which you see here we need to apply some external devices or some external materials through which we can control, like you see various insulating materials are there, mainly you see the springs are there, the dampers are there. These are the like the key elements, or even sometimes you see when we are keeping the masses to suppress the vibrations. So these are the key elements through which we can reduce the vibration amplitude, or we can suppress the vibration rather. So first is the passive vibration control. Second part is the active vibration control. Sometimes you see it is not visible. Say you see the vibration is coming from the internal feature at the microns level, or you see any of the part of the machine, and at which you see here it is not visible to apply these like the vibration controlling devices. Then how do we control? So there are various like the parts which we are like putting under the active vibration controls. So this is the third one. And the fourth one, you see here, when we are doing these things, what are the instrumentation involved in that? How do we first measure those things? And then once we measure these, say, basic elements of vibrations, then how do we what are the instruments involved in that? Say you see if we are on the track side, or if we are on any of the side you see here, and we want to measure that. So what are the instrumentation involved? What exactly the principle involved in measuring those vibrations? So these issues which we are going to deal here in this particular course. So let's begin with first the basics of vibrations, and in this basics of vibration you see here the first, that how we can apply this vibration concept or the dynamics concept to the simple mechanical systems. So we need to like if we want to understand the basics of vibration, we need to go to the basic physics in that. So if we are talking about that, first we need to see that what exactly the science is saying about that. So whenever we are saying that okay something is vibrating, they are also inducing some kind of sound. So sound and vibrations are pretty like the common terms which we always use, and we need to apply the concept that you see why a machine or anything which creates sound is vibrating, or why a vibrating system is creating sound. So the science of sound and vibration is a part of the applied mechanics. So you see here if we are talking about the applied mechanics, then we know that one has to study the behavior of solid, liquid or gaseous media. Sometimes we know that when we are talking about the solid media or two rigid bodies, they are creating so much sound, and the impact at the contact mechanics which we are talking during the impact, they have a huge noise, and there is a clear vibration which is being transmitted through the molecules of that solid body. So when we are talking about that in the solid or the liquid or gaseous media, they are absolutely involving, you see, the deformations, the wave propagation, you see, like you see when I am speaking, we know that at the vocal cord there is a clear vibration, because you see the air which is coming out, it is always being suppressed, and my tongue is like in somewhere oscillatory media. So this wave propagation, when it has like when it is coming out from the mouth, it has some media to go up to the certain level. So starting from the deformation is particular mechanical term in which there is a clear displacement, like at the localized region where the load application is there or any moment or torque application is there. The wave propagation is basically related to the sound phenomena. And then you see here we are talking about the tension and the fracture. They are all, you see, creating some kind of like the mechanics concepts. And when these medias are subjected to the physical agent of various types, certainly you see here like maybe some like various types of the forces or the due to the temperature variation, we know that the sound or vibrations are basically coming into that domain. So sound and vibration fields, in that sound and vibration waves, basically we know that the sound is certainly energy which is always being propagated in terms of the waves. Vibration is nothing but, you see here, that is a molecular phenomena. And you see, when we are talking about any vibrating system, we know that it requires a basic domain or solid media to transfer. Like you see, a basic common example is our mobile. When the mobile is like in the vibration part, and if you are keeping on say some solid surface, when it has, you see, this domain, immediately it will transfer through the molecules of that solid. Or if we are just keeping on the wave in the air open, we know that the affected area is very small. So sound and vibration waves are mechanical elastic waves, and thus you see the condition for their existence are like that the medium possesses mass and elasticity. So you see sometimes when you are talking about the deformation, it's always being like giving some kind of excitation because of the deformation as we are applying, and this deformation mainly dealing with elastic deformation. So in vibroacoustics, there are two classes of waves. One is the longitudinal waves according to the direction, and one is the transverse waves. So you see, like in this particular, if you are broadly speaking about the applied mechanics part, we know that there are two features. One is the fundamental mechanics, which is related to the statics, the particle mechanics, and the rigid body mechanics. In that, you see here, we are mainly dealing with, you see, like that when the body is even in the rest, there are the forces which are being, like under the equilibrium position, and they are being applied to the system. Even when the system is the macro or even the micro, means the particle part. So this rigid body mechanics is always giving that when the two bodies are, or when any body which is being rolling or like sliding or being the contact with the other body of the surface, then certainly there are deforming conditions, and due to the deformation certain kind of excitations are there. So when we applied this mechanical concept to any rigid body or the particle part, we are under the broad category of applied mechanics, in which we have the basic concept of the strength of materials, means what exactly the type of material, what kind of forces are there, how do we resolve these forces, you see, even under the static or the dynamic part. Then even if you are talking about the fluid mechanics, we know that the fluid molecules are always, like travel. There is no, you see here, as such the deformation, but there are displacement. So whenever you see the fluid particles are moving and the inertia force is due to the density feature, they are always being creating, you see, the kind of, like the excitations. Vac formations are there, various things are there related to the fluid molecules. Then vibroacoustics. In the vibroacoustics, we know that the things are being coming right from the basic vibration concepts, and then it is spreading towards the acoustical phenomena. Acoustic emissions are there. So you see here, when we are dealing such things, we know that the fundamentals of sound and vibrations are the part of the broader field of mechanics, with the strong connection to the basic classical mechanics, which is related to the solid or fluid dynamics. And since we are talking about any movement feature or the motion, the dynamics is like one of the basic branch of the physics which is mainly concerned with the motion and the force. When we are talking about the motion feature, we know that we are all talking about the kinematics part. And when like the forces are being involved along with the kind of motion, then certainly the dynamics coming. So you see here, when we are in the domain of dynamics, the first thing is coming how the body is behaving under the motion. So the vibration or oscillation, these are the two common movement is there of the body, can be regarded as a subset of dynamics in which the system is subjected to certain restoring forces like swing back or forth, because to and like the fro motion is there. So how these restoring forces are really controlling that kind of to and fro motion. And then you see like when we are talking about that, okay, this is my like the periodic excitation, the periodic vibration, or you see the pendulum oscillation, then we know that there is an equilibrium position, or there is like the position where you see the body is moving to and fro. So we can say the system is nothing but, the vibrating system is nothing but you see like the assemblies of the parts acting together as a whole from the to and fro motion. And these restoring forces, they are coming due to the elasticity or due to the gravity, which are the two common elements which are always being available when any system is executing its motion or the dynamic phenomena in the real nature. And when this subject, when we are talking about the sound and vibration, it is especially encompasses the generation of the sound and vibration, the distribution and the damping of vibration, that how these like the sound is distributed, how the vibrations are being damped out, what are the key features like through which we can damp out the oscillation or the vibration amplitude, and then the and then how the sound is like the propagating in free field and how it interacts with the closed space. We know that you see here when we are putting like any sound source, and you see when if it has like the source or it has like the media, it will propagate immediately at the very faster rate. So you see here like the physics says that it absolutely, the molecules absolutely requires whatever like whether it is propagating the sound or the vibration, they need the basic domain, the basic structure, the solid structure which like consists of the various molecules, as well as you see its effect on the main and measurement equipment. Because ultimately you see here we know that when we are in the like the noisy environment, what exactly the impact of the common performances on the man, and how do we measure those things. So what are the measuring equipments are there. So technical application like span like even in the wider field from applied mathematics and mechanics to electrical instrumentation, and like in which you see we have analog or digital processing theory, in which like whatever like the signal processing tools are there, to a machinery and the building design. So this sound and vibration is not especially, we can say, restricted ourselves towards the mechanical application only. It can like if we know that some buildings we want to design the building, we need to put various kind of like the sound controlling features, vibration controlling features, because you see like various things are there, and like which can transmit, which can generate the vibration and the acoustic feature. And then you see the like most human activities, when we are coming just towards the human, most human activities involve the vibration in one or other form. You see here they are always being like analyzed based on the dynamic phenomena. Like you see the blood movement is there from the heart. We know that you see when we are running or when we are in the idle situation, the blood motion is different, and through ECG we can simply find out that where is the problem. So this is nothing but a vibration signature only, the movement. Even you see when we are talking about the brain structure, we know that the neurons are all the time, they are just like taking the information and spreading all around. So this is a dynamic phenomena, and we are using the EEG to see the irregularities of this motion. So I mean to say, even when we are dealing with the human part, the ECG, EEG, they are nothing but the signal processing, like we can say tools through which we can analyze the motion of blood or the neurons. So you see like, or else you see, as we can say that when we hear, our endromes you see vibrate, and you see the light waves are absolutely like expanded under the vibrating conditions, and then neurons are getting entire things. Another very common example for the human being is the breathing. Breathing is associated with the vibration of lungs, and you see like the walking involved. Sometimes the periodic, we can say, oscillatory motions are there of the legs and the hands. So this is a great combination of two things, the periodic motion of your legs and hands, and the same time you see here your lungs are also like creating some kind of periodic motions. Or else when we are speaking, say you see I am delivering the lecture, I know that you see here like the sound waves are being generated, this is the energy which is coming out from the throat. But at the same time you see here this like giving a particular direction or whatever the words, articulation, the modulation, all the things are coming out due to the various oscillatory motion of our this larynx, or we can say this our tongue. So in most of the engineering applications, right from you see the machinery to the human being, the vibration is simply we can say analyzed based on the to and fro motion, which is pretty undesirable. So you see like if we are just going back to that, then we know that the Galileo like who discovered the relationship between the length of pendulum and its frequency, that you see how many number of times it repeats its entire motion in a particular time. Then he observed that at a particular frequency, like when it is just related to its natural frequency, the resonance will happen. The resonance is nothing but you see here it has a huge amplitude of the we can say the vibration due to the maximum energy involved there. Here you see here like maximum energy is being transferred towards the system so that it can simply like have the greater motion at an infinite feature. So you see like we can say that natural frequency is nothing but it's an inherent feature of the system, because sometimes when we are talking about the natural frequency of different like any different system, the different systems have different natural frequencies, because you see here it's an inherent property how the system is reacting towards the applied force within its own structure, and accordingly that's why we are saying that the natural frequency is always being coming out due to the free vibration condition. So the vibration may result in a failure of machine or their critical components, because you see here when the amplitude like amplitude of vibration is increases from its limit or the range, certainly you see it can damage, it can even put some kind of plastic deformation, some kind of permanent deviation there. So the effect of vibration absolutely depending on the magnitude in terms of the displacement, velocity and acceleration. These are the three common we can say dynamic parameters through which we can clearly classify the basics of vibrations. And you see here, since we know that the amplitude of these, either the displacement or the velocity or acceleration, are clearly reflecting the vibration significance, we can simply find out that at what frequency this amplitude is there and what is the duration of this much the vibration, that means in terms of how much time is there at which you see this frequency is coming and this much amplitude is coming out from the system. So this is whole you see, if you want to characterize the vibration, now there are two main features in that. One is the exciting frequency and one is the amplitude in terms of displacement, in terms of velocity or in terms of acceleration. So if we broadly classify the vibration, we know that every day we are dealing the vibrations, right from the atomic vibration means the temperature variations. When you see when we are in the common room, you see the room temperature which we are dealing with, it has a common feature all along the room length or the dimensions. But when you like switch on the fan or AC or something, you know that now the temperature variations are there. It is mainly due to the molecular motions, they are interacting, and when they are interacting they are exchanging the energy, and this temperature variation is a basic cause of this molecular dynamics. Second, the human body, the heart, or even like as we discussed about the breathing, or even we are just talking in which the lungs motion is there, or if we are talking about you see like the whatever the speak things are coming out from the human, or else the neuron motion, all these are basically the feature of the vibrations. Then broadly speaking, the machines, even a small machine which say you see we have the fan in our CPU of the computer, it's also creating so much vibration, even it has a light part. Even you see when we are just going to any of our thermal power plant, the huge turbo generator machines are there, the generators are there, they are creating huge noise and huge vibrations. So even the small machine to bigger machine, they are all inducing the vibration, and this vibration is transmitted through any structural media. Then the earthquake tremors, this is one of the good example of our random vibrations. So you see here, right now we are not classifying the vibrations, but you see the vibration can be classified in the discrete level, in the continuous level, or even at the random or the nonlinear features. Then the musical instruments, all these specific tune which is coming out, you see, from any of the musical instrument is absolutely related to the vibrations or the material property of that string. So you see here, like when we are dealing, say if you are driving a motorcycle, we know that huge, like vibrations are being coming out due to the interaction of the tire to the surfaces, and these are being absorbed by various things, and then it is coming to the human part. So like the vibration we are dealing every day. So now if we are thinking from that point, we know that there is a vibration which is there in the system. Now first we are starting from the linear systems. The linear system is a well behaved region, means the systems are always, you see, like behaving in a very proper way. So this chapter is mainly related to the linear system, in which the linear inputs are there and the linear outputs are there, well behaved systems are there. The vibration of any single degree, 2 degree, or even the multi-degree systems with and without damping, they are absolutely like related to this linear system. So we can say that if we want to really understand the basic principle involved in the linear systems, we can start from the single degree of freedom system, in which you see sometimes the damping is there, sometimes the damping is not there. And then we can further go towards, you see here, the 2 degree of freedom system, means like what exactly the coordinates are available in which we can relate the force or the energy terms in that domain. This provides us the degree of freedom, means what exactly the constraints which we are trying to keep to see the force equilibrium feature. And then even in the multi-degree of freedom system, like you see the human body is there, the robotic features are there, or any system in which you see here like the various like the parts of the machine are moving together, then how do we analyze the system in the linear part? So often in the vibration and the acoustic, the calculation of the effect of like certain physical quantities termed as the input signal. Certainly you see, say like we are giving electric supply, so certainly you see now the rotation starts. So this is what our input feature is. This is a well like we can say defined the control input systems are, and when the system is like moving, then they are just like executing the linear output. This means what exactly the output signals are. They are coming in terms of, say if you are talking about the mechanical system, the output may be in terms of displacement, maybe in terms of velocity or acceleration. But again you see there are different devices to record these things. By a single device, say I have accelerometer or I have you see the velocity probe or the displacement probe, I cannot measure by like all 3 quantities by a single device, because there are various other depending parameters are there in that. So now if I am coming back to the like the linear system, you can see that you have a figure on your screen in which you see we have the input signal. The input signal can be in form of the dynamic force F, which is a function of t. We may have you see the velocity as an input, we may have the pressure as an input, or we may have the velocity as you see again the input. So you see in any of the combination, right from force to velocity, pressure to velocity, these are all you see like the key input parameters. And if the system is linearly time invariant, then certainly we can say that the system is not inducing any kind of like the non-linearity in the system. It's a well behaved region. So we may expect certain output from that, say you see even in terms of force or velocity, in terms of pressure or velocity in that. So linear time invariant system simply describe the relationship between the input signal to the output signal. And then you see here, since as I told you that no nonlinearity is involved in that, then we can say that you see since it is a single degree of freedom system, we can say the force input, force output can be easily related. Even the velocity input, velocity output can be easily related. So if the coefficients are moreover you see independent of time, certainly you see here we are not trying to relate with the time itself, then we can say the system is also the time invariant, and a linear system have several important features in this, because you see here it's a well behaved part. Like you see when we are talking about the elastic deformation, where the Hooke's law is valid, we know that whatever the parameters are, there may be force with the deformation, stress with strain, or anything, or under the like we can say the Newtonian mechanics, when we are saying that the Newton's law are applicable, we can simply say that they are absolutely valid towards you see like the elastic feature, where the linear propagations are there, the linear like we can say the systems are there. Let's focus on one example. Now I am going to show you the one of the basic feature of our like the automobile systems, where number of inputs are there. So it doesn't matter, you see, that you always have to have, you see, like the one kind of input and one kind of output. There may be more than one inputs are there. There may be more than one outputs are there under the linear actuation of the system. So you see here, like we have, just I am going to show you that the automobile which has various inputs, the number of inputs are there of the linear system and the outputs are there from the vibration velocities. And these vibration velocities are then again we are trying to feed as the input to the various linear systems, and we can find the outputs as a pressure sources. So you see that this one, in which it is very clear that you see, this is what my force is, the input forces are there, and when the forces, you see, on a vehicle, there are various forces, right from the engine to the air drag, the lift forces, various, you see, like the dynamic forces are there, even the forces which can be generated due to the excitation you see at this. So you can see that we have various force regions are there which are coming out due to, we can say, drag forces, these forces. So this is what the all input forces. When they are coming to that, you see here at this particular feature, now we have various vibrations velocities. Means you see here there is an excitation at this particular part due to the motion of the vehicle. And when you see this part, when it is being coming to the human being, this is basically, you can see that a kind of input to the human being as a vibration velocity input. And then you see, we can see that, you see how much the pressures are being there at we can say in terms of sound pressure or in terms of anything. So by adding up the various contributions from all the significant excitation forces, the total sound pressure at the point of interest is nothing but the passenger's compartment. And we can just see that what exactly the comfort levels are being there due to the excitation of various forces which are being termed into the vibration velocity and then into the sound pressure. The engine is also we can say fixed, and you see through this chassis, this is basically the media which is being transmitted that, and through which you see we can apply the vibration isolators as well. So what we can say that you see various forces which we have shown in the previous diagram, right from the F1 force which is influences through the chassis 1, we can put any linear actuation feature, and the velocity difference will certainly give you the kind of vibration excitation. So a linear oscillation in the mechanical system can be considered here, and whatever the oscillations are coming into the system is absolutely giving us the linear relationship between the exciting forces and the resulting motion. And since there is a linear feature, so there is a pretty well defined output is there, as that as we can describe in terms of the basic three dynamic properties, the displacement, velocity and the acceleration. And then you see even in that we can further add these contributions which are just coming out in terms of you see the vibrations, in terms of the vibration velocities from these forces, then it can be simply converted into the velocity component, and then it can give simply this one. So when we are talking about the two main features, we know that the linearity is a basic property of the system through which you see here we can simply propagate, we can make a proper relation of the force or the velocity or sound pressure in that way, and we can apply the various the coefficient which can relate, like you see in the Hooke's law we have the Young's modulus, like in Newtonian's law we have the Newtonian coefficient, you see it's like the viscosity, or in any of the term these the linear variant features can be straightway relate using some of the coefficient. Now we are going towards one of our basic case, that is the single degree of freedom system. So in that, the single degree of freedom system is very, very essential in such a way that we just want to study the information about how the system characteristics are really influenced by the various different quantities. Because if we are just taking the various other parameters, then sometimes we are not in a position to analyze the dominant feature of that. Maybe you see sometimes the lower amplitude of some exciting part is more important. So that's why you see sometimes we need to constrain the other feature and just to see a single degree of freedom system analysis. So moreover, one can model even the more complex system provided that they are they have the isolated resonances as some of the single degree of freedom systems. So that's why, as I told you, that the other features can also be influence the parametric excitations. So we need to just see that what exactly the dominant features are. Most of the system exhibit simple harmonic motion or the oscillation, the periodic oscillation. So these systems are like said to have the elastic restoring forces, in which you see like the restoring forces are nothing but you see some kind of like the constraint against the motion, like you see the spring. The spring forces are always coming under the restoring forces. The gravitational forces, these forces are always termed as the restoring forces, and such system can be easily modeled as I am going to show you a simple spring mass system, where you see there is no damping through which you see here, or the damper through which we can damp out the oscillation amplitude or the vibration amplitude. This constitutes the most of the basic vibration model of the machine or any structure you see here, and can be successfully described the any like various number of the surprising like number of the devices, machines, or any kind of the structures. We can straightway apply this. So now you can look at that, you see we have a simple spring and the mass system, and when you see here we are trying to disturb the mass, certainly it will like deviate from its position, or we can say it has a clear displacement from its position, and through which you see the various forces are being generated. And if we are saying that it is under the equilibrium position, that means these forces are well balanced. So this system provides a simple mechanical model that seems to be more sophisticated than the like we can say any problem requirements. So this system is very useful to conceptualize the vibration problem in different machine components. So you can see that what we have a spring system, and the spring is always being characterized using the stiffness. The stiffness is like giving you the kind of again the material property. Also it is giving that how much force it can sustain and how much deformation can be generated according to the applied force. And then this is you see the mass is hanging from the like the mass is hanging over the spring, and when there is a displacement, say x of t, when the displacement is being given or the disturbance is given to the mass, there are the two forces which are being clearly generated here. One, the inertia force as the movement of mass, so mx double dot is there, this one. And then you see on top of that, because you see here this is under equilibrium position, so you see on top of that we have like the restoring forces. And when they are like we can say, if we are just putting the free body diagram, we know that both are just balancing each other. And when they are balancing each other, we can simply say that the equation of motion is nothing but equals to the sum of inertia force and restoring forces are equals to 0 because of the equilibrium systems. So say that you see here, if we have the displacement x equals to x of t, and then the mass which is just like moving periodically like under the excitation of this feature, then we can say the equation is mx double dot plus this like kx plus xx and this mg. This weight is also sometimes adding one of the additional feature in terms of force. So k is the stiffness, which is a material property of the spring you see here, which can be like get using Newton per meter. The xx is the static deflection, we disturb and leave it like that. The mass is nothing but you see the in kilogram, the g is the gravitational acceleration, and you see the acceleration is this one, x double dot. So the inertia force is, because the mass is there which is moving at the acceleration x double dot, we have mx double dot as the inertia forces. So when we apply like the static conditions on that, then certainly you see we are ending up with the equation mx double dot plus kx equals to 0, and this is one of the basic equation for single degree of freedom system. And you see here we know that it is a linear equation, because all the term x double dot and the x, they are simply posing, and means acceleration or the displacement, they are just giving the linear actuation to the system, and it is a second order ordinary differential equation because it is a discrete system. So we have ordinary differential equation with the constant coefficients. So simple experiment we can simply perform to find out the spring stiffness, because we know that the spring stiffness is coming under the elastic deformation. So we can get you see here with the force deformation relations, or you see with the stress strain relations as well. And you see how we can get, you see now we are going to see, this is what the experiment is. We have a simple spring which has the initial displacement x0 without having any additional feature of the mass in the first diagram. Then you see here when we are adding up the mass, we know that this is the known value of mass, and with that you see here this is what the dotted line is showing my static like the equilibrium position. And when we add any known mass, the certain amount of deformation is being there within the spring itself. So, you see here when it is just coming down there, again we are adding the another same amount of mass. You see here there is like the deformation is x2. So, what we have x0, we have x1 when the one mass is being added, and you see the x2 when the two masses are being added. So, you see here like this is a linear integration of the mass, and corresponding deformations are being there, the elastic deformations are being there in the spring. So, as a result of this static experiment, means there is no, you see here, the dynamic feature of any of the things. Then you see we can simply plot what the force is. This is what my inertia force, even you see because it is coming down, versus you see the slope, means the value of the displacement. So, you can look at that, you see here after a certain part, you see we have the linear and the non-linearity feature is being added. This is what the realistic nature of the spring is. Up to even the elastic deformation, which is like the Hooke's law is saying that after a certain point there are, you see like the slopy feature has come. So, up to the linear propagation, you see when we are simply dropping, say this is what my displacement and the force, we can get, you see here like the spring stiffness by force per unit deformation under the elastic feature, means the straight line. So, once m and k, the mass is known to us, the k is known to us. Once we get those things, we can solve the equation, because you see this is what the simple harmonic motion. So, we can apply a simple like the solution feature as we are applying to any ordinary differential equation. With the time history of the position of mass with the initial position, means if we have the initial position and initial velocity like of the mass, we can directly give as the input x0, and you see here whatever the v0 is there. And the form of solution of the previous equation found from the substitution of of all these parameters, as we are assuming that the motion of the spring of the mass which is constrained by the spring is of the periodic motion. So, you can look at that, you see x of t, this is what my displacement outcome is nothing but equals to a sine omega t plus phi. A is the amplitude, omega n is my like the natural frequency, and as I told you, the natural frequency is the system's inherent property, like because you see through that the system is exciting at the free vibration level. So, you can see that it is nothing but equals to square root of k by m. K is your spring stiffness and m is the mass distribution of the system itself. And then you see you have sine, because it is a harmonic feature. So, you have sinusoidal feature of omega and t plus phi. Phi is the phase shift. Then you see a and phi, like we can simply find out like the constant like through the integration by applying all the boundary condition or the initial conditions. So, if x0 is the like we can say specified initial displacement, the known one parameter from the equilibrium, and mass m and v0, which is again you see the known parameters to us, we can simply get the displacement x of t is nothing but equals to square root of omega n square x0 square plus you see here u square by omega square sine of this thing. This is what my generalized solution. As we know that in the ordinary differential equation, there are two main parts of the ordinary differential equation solution. One is the particular integral and one is the complementary function. The complementary function is mainly responsible for free vibration concept, and particular integral is mainly responsible for the forced vibration. So, through that you see here you have both the thing, x of t is nothing but equals to v0 omega 0 sine omega n t plus x0 cos omega n t. So, you see both the things have been like included there, and when we are now substituting the displacement as a periodic input is c into e to the power lambda t, you can find that you see here we can simply get the equation 1.5 as m lambda square e to the power lambda t plus k into e to the power lambda t equals to 0. We know that you see like this cannot be the whatever the coefficient, the c which is the amplitude feature cannot be 0. Certainly we have the e to the power lambda t equals to 0. That means you see here finally we are ending up with the equation of m lambda square m into lambda square plus k equals to 0, or the lambda is nothing but equals to plus minus j, which is the unit vector, square root of k by m. This square root of k by m is the system's property through which you see we are getting the eigenvalue, or we can say the characteristic root of the equation. We are referred that as like the natural frequency. So sometimes when we are trying to map this into the mathematical description, we know that the this natural frequency is nothing but the eigenvalue of any characteristic equation, or it is nothing but the characteristic root of the basic equation of the system. So we can say that this is like the j is nothing but the imaginary feature, and it is always reflecting from plus minus j, you see here. So when we are trying to put this one, we know that we have a generalized solution for this is x of t is equals to c1 into e to the power omega n jt plus c2 e to the power minus omega n jt, where you see we have both, this e to the power omega and c1 and c2 basically are, which is related to the e to the power omega n jt n minus term, are arbitrary complex conjugate terms which can be easily get using the integrands. The value of constants either you see can be again you see can be easily achieved using the boundary condition and the applied conditions of the feature. It all depends on that. So this is you see here one of the basic system in which you see we are not applying any kind of decay of the amplitude of the vibration. We are only applying that when the any system is under excitation, then how the system of the mass system and the restoring forces, means the inertia force and restoring forces are interacted, how we can get the generalized solution of such kind of systems when they are just simply forming the equations of motion. Now we are adding the damper as one of the feature, because we know that even when the system is exciting, it does not have you see the infinite oscillatory feature. There is always you see some decaying feature is there, and this decay is mainly due to the damping part. So most of the system will not oscillate, as I told you, indefinitely when it is being disturbed. Either you see it has some kind of the mechanism through which these oscillations are being dying out. Typically the periodic motion damped out after some time. The easiest way to model this in terms of mathematical way is just put the damping force along with the restoring forces and the inertia forces. So when we are applying this to the same basic system in which we have the mass, spring and damping, we can say that there are three forces. One, when the mass is moving, due to the disturbance is always at inertia forces, mass into acceleration. When the spring is there, certainly the restoring forces are coming out, and it is equals to k into displacement. And when the damping is there, through damper, maybe the dampers are of various kind, which we are going to discuss in later form. We are right now saying that if it is a viscous damper, certainly you see here whatever the forces which are being coming out due to these the viscous dampers are viscous forces, and they are nothing but equals to viscous coefficients into velocity. So and you see the system is under equilibrium conditions, that means you see here mx double dot plus cx dot plus kx equals to 0. Physically the addition of despot or the damper, which always results in the dissipation of the energy. It always dissipates the energy, and that is how you see we can control the oscillatory movement. So you see, you can see that now this is what our the system is. We have the system, the mass same, the spring and the damper, and these are you see all the forces are that you can look at that mx double dot is there, plus you see the the damping coefficient and the interaction of this the velocity of you see x double dot and this one, and then you see here we have the spring coefficient k, and this is you see the x and x0. And when we are just trying to make balance of this, we know that we can get the basic equation which we discussed already. So if the despot exerts a dissipative force proportional to the velocity on the mass, certainly we know that whatever the dissipative energy which is being there, it can be easily absorbed there. So unfortunately the constant of the proportionality, the C, which is the basic property of the damper, cannot be measured by the static method, because in that you see here we have, just like you see in the spring, it was a simple linear we can say the displacement part, but here we have the velocity term. And this C, which is the property of the velocity, the C is nothing but the constant, damping constant, it is a property of the velocity. And this velocity, when we are trying to see, it not only depends on the amplitude, but also depends on the frequency feature. So you see here we can get and again you see in the damper, if you look at the damper configuration, we know that there is a viscosity feature involved in that what is the oil which is being there in the viscous part, and what is the viscosity is there of this viscous damping. So now you see here, now if we are just going towards again the same harmonic motion, we know that this this whatever the oscillation is there, it's a periodic one, and x of t is nothing but equals to a into e to the power I x. And then we are keeping that, you see, in the same equation mx double dot plus cx dot plus kx equals to 0. We know that we have a into m lambda square e to the power lambda t plus c lambda e to the power lambda t plus k into e to the power lambda t equals to 0. And here when we are keeping a equals to 0, we know that this cannot be equals to 0 e to the power lambda t. So then you see we are ending up with the equation m, the inside of the bracket e into m into lambda square plus c lambda plus a k equals to 0. We can make this equation by dividing the mass just to keep the characteristic generalized equation. So we have lambda square plus c by m into lambda plus k by m equals to 0. And when we just trying to solve using like the characteristic equation, we have the characteristic roots are there lambda 1 comma 2, which is nothing but equals to minus c by 2m plus minus square root of c square by 2m square plus minus 2 times of k by m. Or else you see here when we are just trying to see this, we know that the c by m k by m is giving a very specific characteristic of that, which we are going to discuss. The quantities under the radical is called the discriminant, as we know that, and the value of this discriminant decides whether the roots are real or complex. So you see here now we are going to first define the terms involved in that. One is the damping ratio. The damping ratio is nothing but equals to, as like the term itself speaks, that the damping, there are two different dampings are being involved. Like one is the C is the applied damping, which we are just trying, which we are applying trying to reduce the vibration amplitude, and CC is the critical damping. Critical damping is one of the minimum damping, you see, which should be there to reduce like the oscillation at the minimum time. So like it is relatively convenient to define the non-dimensional term, you see, as this one, and it is nothing but equals to C by Cc, as I already told you, and we can simply say that the damping ratio is nothing but shown by the zeta. Zeta is equals to C by Cc, where Cc is nothing but equals to 2 times of square root of Km. So you see when we are keeping this, now our equation, when we are trying to keep this Km and C replaced with the omega n and this one, we know that omega n is nothing but equals to square root of k by m, and zeta is nothing but equals to C by Cc or C by 2 Km. Now we can replace this equation as x double dot plus 2 zeta omega n x dot plus omega n square into x equals to 0. When we are now, this is my characteristic equation, which is representing a single degree of freedom system with the spring and damping. Now it has the two characteristic roots, lambda 1 comma 2 is nothing but equals to minus zeta omega n plus minus omega n zeta under square root of zeta square minus 1. Or else I can replace with this minus zeta omega n plus minus omega d. Omega d, now you see my system, which has the damper as one of the essential element, now it has two different frequency. One is the natural undamped frequency and one is the natural damped frequency. And we can relate both the things, that the natural damped frequency is omega d equals to omega n square root of 1 minus zeta square. And you see here, like with this particular concept, we can easily find out that what is the value of zeta. Zeta is nothing but the damping ratio, which has a physical, like we can say relation. So it can clearly give that, you see here, if we are going towards the damping, over damping, critical damping, under damping, what exactly the kind of features which we require, and accordingly we can give the system properties. So like we can get, you see, straight away that how the system will behave, what exactly the type of like the damping should be provided, and then how much the excitations will come out from that. So now if we apply this concept to the real physical system, say this is what you see the basics of vibration when we are applying to any physical dynamic system. Say this is my the two wheel vehicle is there. We have the rider, we have, you see, like the vehicle itself. This is my physical dynamic system. Now I just want to go to analyze the motion. So these are the basic steps which I need to follow strictly. One is, first I need to map this physical system into the real mathematical features. And when I am trying to do this, I need to see that what I have. The input variables which I have right now is the mass of rider, mass of vehicle. the two masses are there. Then what I have in other terms, the tires. The tires are absolutely in the contact of the road, so they are in the deformation, and this deformation can be straightway replaced by the spring. Other thing, when the rider is just sitting on the seat, there is a clear interaction between the base part of the rider and the seat part. So there is a deformation. So I can also replace this as the spring. And then I have, you see, the struts are there. You can see that on the diagram, these are the struts. So these struts have, you see, the damping features. So I have the dampers. So this physical system is clearly reflecting the three basic modes: mass, damper, and the spring. And now I can relate these things with my three basic dynamic properties: displacement, velocity, and the acceleration. So I can first, you see here, equate that what exactly the replica in terms of that's what we discussed about the mass, spring, and damper. So we have the equilibrium mass, as I told you, the rider mass and the vehicle mass. Second, we have the equivalent stiffness, the stiffness of two tires, the stiffness of even the contact region between the human body, means rider, and the vehicle part. And then we have the damper. The two struts are there, the front wheel and the rear wheel. So you see here, this is the equivalent feature. And then you see, when we are trying to map into the other part, that is because we want to generate the third part, is the equation generation, that what exactly the equation of motion is there. So you see here, we need to first put the force balance condition. So on the mass, we have all three forces: the inertia forces, restoring forces, and the damping forces, as we can describe here. And once you have this, you have now the equation of motion, as we discussed already, mx double dot plus cx dot plus kx equals to 0. And once you have these things in terms of the single degree of freedom system, we can simply find out this, and then we can apply, since it is a periodic motion which we are assuming, or a simple harmonic motion, we can apply the input part x of t is nothing but equals to c into e to the power lambda t. And when we are keeping that part, we can have the solution, the characteristic roots, which are simply giving us the eigenvalue, or in other terms, we are having the exciting frequencies of that. So in today's lecture, we discussed about the basics. What is the importance of the vibration is? Why we are dealing all basic mechanics concept when we are talking about the vibration. And then you see here, when we have any physical real system, how we can relate the real physical system towards the mathematical formulation. What are the basic, we can say, the terms are there which are always being a governing terms for the exciting vibrations. And as I told you that, remember, there are three basic dynamic parameters which are always being responsible for having any kind of excitation in the system: the displacement, the velocity, and the acceleration. And if we want to measure these things, we need to have three different devices for that. So you see, in this particular lecture, that's what we discussed. In the next lecture now, we are going to deal with the 2 degrees of freedom. As you see that in this particular screen, we have the rider and the vehicle. And this system is absolutely for, right now, the single degree. As you know that we have a single mass, single, like the damper, and the we can say the k, which are being there just with the x. And the x is the horizontal or vertical movement just in one direction. But we know that, you see here, this is not a correct, we can say, the conversion of this. We may have, you see, a different displacement of, say, like the rider or the vehicle. We may have, you see, like the different stiffness at the, like the rider to a seat, or this tire to this one road. Or we have, you see, the different damping from rear or front struts. So when we know that these things are quite feasible, we need to now see towards the other features of that, is the 2 degrees of freedom system, without damping, with damping, and then we are trying to solve mathematically about the real physical system. Thank you.